Hello dear students, this is our lecture for Mathematical Statistics course. As we mentioned before that we will take today moment generating functions. We have seen in the last or previous lectures that there are some distributions such as geometric whose moments are difficult to compute from the definition. A moment generating function is a real valued function from which one can generate all the moments of a given random variable. In many cases, it is easier to compute various moments of x using the moment generating function. The first definition today is: let x be a random variable whose probability density function is f of x, a real valued function. M is element in real numbers defined by m for t, which is equal to the expected value for e with power t of x, t and x, t times x, is called the moment generating function of x if this expected value exists for all t in the interval t is between minus h and plus h for some h is greater than 0. In general, not every random variable has a moment generating function, but if the moment generating function of a random variable exists, then it is unique. At the end of this section, we will give an example of a random variable which doesn't have a moment generating function. Using the definition of expected value of a random variable, we obtain the explicit representation for m of t as m for t is equal to summation for x element in real numbers or the range of x for e with power t times x times f of x if the x is discrete, and integration from minus infinity to plus infinity to e with power t times x times f of x dx if x is continuous. For example, let x be a random variable whose moment generating function is mt and n be any natural number. What is the nth derivative of m of t at t equal 0? The answer is, we have the first derivative d over dt for mt, which is equal to d over dt for the expected value of e with power tx. The expected value for the derivative of e with power tx is equal to the expected value of x times e with power tx. Similarly, the second derivative for mt, or the moment generating function, is equal to the second derivative to the expected value of e with power tx is equal to expected value for the second derivative for e with power tx, which is equal to the expected value for x squared times e with power tx. Hence, in general, we get the nth derivative for m of t, or for the moment generating function, is equal to the expected value for x with power n times e with power tx. If we set t equal 0 in the nth derivative, we get the nth derivative for the moment generating function when t is equal to 0, which is equal to e, or the expected value for x with power n. Hence, the nth derivative of the moment generating function of x evaluated at t equals 0 is the nth moment of x about the origin. This example tells us if we know the moment generating function of a random variable, then we can generate all the moments of x by taking derivatives of the moment generating function and then evaluating them at 0. For example, what is the moment generating function of the random variable x whose probability density function is given by f of x is equal to e with power minus x for x greater than 0 and 0 otherwise? What are the mean and the variance of x? The moment generating function of x is equal to expected value for e with power tx, which is equal to the integration from 0 to infinity for e with power tx times f of x dx. This integration will be equal to finally 1 over 1 minus t if 1 minus t greater than 0. The expected value of x can be computed from the moment generating function as following. The expected value of x, or mu, is equal to the first derivative for the moment generating function when t is equal to 0, which is equal to 1, and the expected value for x squared is equal to the second derivative of moment generating function when t is equal to 0, which is equal to 2. Therefore, the variance of x is equal to the expected value of x squared minus mu squared, which is equal to minus 1, which is equal to 1. Another example, let x be a continuous random variable with density function f of x is equal to b times e with power minus bx for x is greater than 0 and 0 otherwise, where b is greater than 0. If the moment generating function of x, then what is the moment generating function for minus 6b? The moment generating function for the expected equal to expected value of e with power tx, which is equal to integration from 0 to infinity for b times e with power tx times e with power minus bx dx, which is finally equal to b over b minus t if b minus t is greater than 0. Hence, the moment generating function for minus 6b is equal to b over 7b, which is equal to 1 over 7. Another example, let the random variable x have moment generating function equal to 1 minus t with power minus 2 for t is less than 1. What is the third moment of x about the origin? The answer will be to compute the third moment. We have to get expected value of x with power 3 of x about the origin. We need to compute the third derivative of the moment generating function at t equal 0. The first moment generating function, or the moment generating function, is equal to 1 minus t with power minus 2, and the first derivative is equal to 2 times 1 minus t with power minus 3, and the second derivative is equal to 6 times 1 minus t with power minus 4, and the third derivative is equal to 24 times 1 minus t with power minus 5. Thus, the third moment of x is given by the expected value of x cubed, which is equal to 24 over 1 minus 0 with power 5, which is equal to 24. Proof. Let m t, or the moment generating function, be the moment generating function of the random variable x. The Taylor series expansion of moment generating function about 0 is given by the following formula. Since the expected value for x with power n is equal to moment generating function with power n for 0 for n greater than or equal 1 and m0 equal 1. From 4.3 and 4.4, equating the coefficients of the like powers of t, we obtain en equal to expected value of x with power n over factorial n, which is equal to factorial n, which is expected value of x with power n is equal to factorial n times an. This proves the theorem. Another example, what is the 479th moment of x about the origin if the moment generating function of x is 1 over 1 plus t? The Taylor series expansion of moment generating function, which is equal to 1 over 1 plus t, can be obtained by using long division, which is equal to the following formula. As we mentioned before from theorem 4.5, the expected value for x with power 479 is equal to 479 factorial times a 479, which is equal to minus 479 factorial. And thank you.